Good morning, students. In previous class, we have seen about bipolar junction transistor, that is BJT, and we have seen the bipolar junction transistor at a different configuration. As I said earlier, we need two input terminals and two output terminals. So on that basis, we are classifying the bipolar junction transistor classifications as common emitter, common base, and common collector configuration. And these configuration, we analyzed the characteristics with input and output signals, so we term it as input and output characteristics. So, and also I have given assignment on junction field effect transistor yesterday, and today we are going to see about transistor biasing. So for faithful amplification, the following conditions must be satisfied in transistor biasing. So first two conditions we already know. I am repeating these conditions throughout this transistor classes. So your first condition is emitter bias junction is always forward bias. That is, positive terminal of the battery is connected to P type of semiconductor, and negative terminal of the battery is connected to N type of semiconductor. And the collector based junction is reverse bias. That is, positive terminal of the battery is connected to N type semiconductor, and negative terminal of the battery is connected to P type semiconductor. And one more condition has been added in transistor biasing. That is, there should be a proper zero signal collector current. That is, the collector current should be a proper zero signal current, and the definition for this is given below. So the proper flow of zero signal collector current and maintenance of your collector emitter voltage during the passage of your signal is known as transistor biasing. And while following this transistor biasing, stabilization is to be maintained. So what is stabilization is the maintenance of operating point as constant throughout the process of your biasing is known as stabilization. So we use two types of stabilization. One is stabilization or two techniques for your stabilization. One is stabilization technique and other one is compensation techniques. We use these two techniques while maintaining the operating point as constant. So the first technique is stabilization technique. In this technique, the biasing current will permit the variation of base current so as to maintain the collector current as constant. Our aim is to maintain collector current constant. So this collector current is maintained constant by varying the value of base current, and other factors like reverse saturation current ICO, current gain beta, and base emitter voltage variation are also are not included over there. And coming to compensation technique, this technique is very sensitive devices such as diodes, transistors, your thermistors, etc. And also such device will produce the compensating voltage and compensation currents in order to in such a way that the operating point will be maintained stable. So these two techniques are used for maintenance of the operating point as a constant value. And coming to stability factor, while talking about stabilization, the different compensation stabilization techniques, the comparison of biasing circuit with a common factor is called a stability factor. So we are going to compare all this biasing circuit with a common factor. That factor is termed as stability factor. So the stability factor depends on different values. First one is stability factor S. That means it is going to depend on your reverse saturation current ICO. And second stability factor is going to depend on current gain beta and maintaining other factors constant. That is, your voltage and your reverse saturation current will be maintained constant in S beta. Whereas in stability factor SV, your voltage is varied, but your gain and reverse saturation current will be maintained constant. These are the three stability factors. And coming to the equation of your stability factor, expression for your stability factor. So for first, with respect to your reverse saturation current ICO, S is equals to differentiation of IC with respect to the differentiation of reverse saturation current. That is, only the reverse saturation current value is alone changed in order to change the value of your collector current. So it is also can be mentioned as ratio of change in collector current to the ratio of change in reverse saturation current, keeping your current gain beta and base emitter voltage VBE constant. And coming to stability factor S beta, it is equals to differentiation of IC with respect to differentiation of beta, that is change in ratio of change in collector current with respect to ratio of change in current gain, maintaining your saturation current and base emitter voltage as constant. Coming to stability factor of SV, SV is the differentiation of IC with respect to differentiation of your base emitter voltage, that is also been denoted as ratio of change in collector current with respect to the ratio of change in base emitter voltage, keeping your saturation current and current gain as constant. And doing this transistor biasing, we use different methods. Method 1 is base resistor method or fixed bias method, and method 2 is collector to base bias method, and method 3 is voltage divider bias or self bias method. By using these three methods, we can do transistor biasing. And your next topic is operational amplifier. We generally call it as op-amp. And your operational amplifier is an analog device which is used to do some mathematical functions. The mathematical functions will be like addition, differentiation, integration, etc. And the starting stage, earlier while inventing the operational amplifier, it is constructed with a very big vacuum tubes which is worked at high voltages. So we have faced many disadvantages on that circuit, and the main disadvantage of that circuit is it is going to be very large. And while the size is very large, the construction cost will also be more expensive, and as it is going to work at high voltages, it is going to consume more amount of power. But today's operational amplifier it is made of linear integrated circuits. We have seen it in labs. So it is made of linear integrated circuits that use relatively very low DC power supply. Only we use battery supplies for that, and it is also going to be reliable and inexpensive. And the basic internal structure of the amplifier, that is, it is an integrated circuit. While the circuit is integrated with your resistors and capacitor combination and transistors provided inside that integrated circuit, and these are properly interconnected in a compact form called as integrated circuit. And this first op-amp integrated circuit was developed by Robert J. Wilder at a Fairchild Semiconductor Company in early 1960s. In 1960s itself, the integrated circuit operational amplifier has been invented. So the basic classification of operational amplifier based upon the type of input signal given to the amplifier, it is classified into inverting amplifier and non-inverting amplifier. We see how the input is given to the operational amplifier with the help of the block diagram in the upcoming slides. And ideal operational amplifier, we have seen what is the function of amplifier when it was invented, everything we have seen, and how an ideal operational amplifier will work. Our operational amplifier is a very high gain differential amplifier with high input impedance and low output impedance. So generally your operational amplifier will be having very high input impedance, and the output impedance will be very low. And these operational amplifiers are used in various applications. Some of the main applications are your oscillators, your electronic filter circuits, and instrumentation circuits, etc. These they were used to provide the voltage amplitude change. That is, amplitude and polarity can be changed with the help of operational amplifier in these applications. And as I said earlier, it is going to perform the mathematical operations like addition, differentiation, multiplication, comparison, integration, etc. And this is the symbol of your operational amplifier. It has two input terminals and one output terminal. The two input terminals are nothing but your inverting input and non-inverting input. Based upon the input given only, it is classified as inverting amplifier and non-inverting amplifier. So the inverting input is given to the transistor, then it is called as inverting amplifier. If non-inverting input is alone given to the operational amplifier, it is termed as non-inverting amplifier. And this is the equivalent circuit of your operational amplifier it is equivalent circuit. We have two resistances, input resistance, output resistance, and voltage gain source, that is AVD, that is differential voltage. The operation of differentiation is happening here. So differential voltage is given here, and where your V0 is output voltage, V1, V2 are input voltage, and Rn is input resistance, and RO is output resistance, where VD is differential voltage, that is V2 minus V1. So output voltage is equals to your gain into the differentiation voltage, that is V2 minus V1, so which is equal to A into VD. And here are the characteristics of your ideal operational amplifier. So it is going to have very high input resistance and very low output resistance. That is, input resistance will be infinite and output resistance is 0. Whereas it is going to have high loop gain. A is going to be infinity, and input bias current IN is equals to 0. And when the input voltage V1 is equals to V2, then output voltage V0 will be equal to 0. Why? Because when we know that it is doing the function of differentiation, so V1 minus V2 will become 0. So at this condition, the input offset voltage and the input offset current will be equal to 0. And also the bandwidth will also be equal to 0 for all the frequencies, and it is going to have infinite common mode rejection ratio. The rejection ratio will also be infinite. And infinite unity gain frequency. The unity gain frequency will also be equal to infinity, and slew rate will also be infinity. These are the characteristics of ideal operational amplifier. And coming to the block diagram of our operational amplifier, it is classified. It is divided into 3 blocks. One is input stage, middle stage, and output stage. Each stage is going to perform different functions. Like your input stage is going to perform your differential amplifier function, that is V1 minus V2 or V2 minus V1. And middle stage is going to perform the gain circuit. It is going to add the gain to that particular circuit. And output stage is the emitter follower. It is going to do the load compensation. And input stage definition, explanation is given here. There are 2 inputs, we all know. These 2 inputs will provide amplification to the difference in the voltage between the inputs. And the basic requirements of input stage, we have seen the characteristics. On those characteristics, the input characteristics alone is mentioned here. It is going to have high input impedance, low input bias current, high input impedance of that will be greater than or equal to 10 kilo ohm, and low input bias current of less than 0.5 micro amp, and low input offset voltage, that is less than 10 millivolt, and low input offset current, that is less than 0.2 milliamp, and high common mode rejection ratio, that the CMR will be greater than or equal to 70 decibels, and this stage will be able to suppress the undesired noise which is common to both the input terminals. The noise will also be suppressed at this stage. Coming to middle stage, it is a gain circuit. We all know, and it is used to provide some excessive voltage gain for output stage, and generally the feedback capacitor is used in this stage to provide your frequency compensation. Frequency compensation is also done in middle stage with the help of your feedback capacitor. And coming to output stage, it is the emitter follower, as I said, and the high gain output is fed to the input of the emitter follower, and this stage is mainly used to avoid the excessive loading effect of the input stage. The excessive loading, what happens in the input stage, as I said earlier, the input impedance is high, so excessive loading happens there. So it has been avoided at this stage, and it produces substantial amount of power into the low impedance load. And some of the basic requirements of your output stage are high output current and low output impedance, short circuit protection, and less standby power. And now see the characteristics of IC741, which is a general purpose operational amplifier we use. So the features are here. It is a bipolar operational amplifier, we know. It is a general purpose amplifier. It is widely used general purpose amplifier. Why it is used as general purpose amplifier? Because it is going to have low power consumption, and short circuit protection will also be there. High input voltage range, that is voltage range can be varied to high values, and no external frequency compensation is required in this IC741, and offset null capacity will also be there. And large common and differential mode voltage ranges will be present in IC741. There will be no batch problems, and overload protection on input and output circuit will also be provided using IC741. And there will be excellent temperature stability. These are some features of your IC741. And coming to the types of amplifier, inverting amplifier, as I said earlier, here only the inverting input is given to the circuit and non-inverting input is grounded, that is V2 is equals to 0. So the output voltage is the feedback of inverting input through the resistance. We are connected to resistance. One is feedback resistance RFB and the other one is resistance R1. This feedback resistance is connected between the output voltage to the input voltage. That is what is mentioned here. And the current through this input resistance R1 is given by I1 is equals to V1 minus V2 divided by R1, where V2 is equal to 0, your input current will become V1 by R1. and your operational amplifier will draw no current. So your output voltage will be equal to minus I1 into RFB, that is V1 divided by R1 into RFB, that is your input current into your feedback resistance. So output voltage is equal to input current into feedback resistance, and gain of inverting amplifier is given by your output voltage and input voltage, ratio of your output voltage and input voltage. And